Although I do really hate putting on sunscreen, I have to say that the idea of billions of tiny little quantum mechanical shields protecting me is really cool. You've probably realised that as soon as the sun comes out here in the UK, somebody is going to say, put your factor 30 on, and probably they've got good reason for this. The UV photons in the sunlight have a lot of energy. How is it that a simple sun cream can reduce these effects? People suggest it's to do with reflection or perhaps with some mysterious blocking effect. But in this video, I'm going to show you that it's a simple quantum mechanical effect that rescues you from potential damaging rays every time you use it when you go out in the sun. In organic sunscreens, quantum mechanics comes to the rescue by enabling bound electrons within molecules to jump to higher energy levels. Think of a standard atomic energy level diagram. You have a ground state and several other states up above that. When an incoming ultraviolet photon strikes a bound electron, it can be absorbed if and only if the photon energy matches the exact gap, in this case delta E. In simple atomic physics, an excited electron drops back down by emitting another photon. But in complex organic molecules, instead of the absorbed energy being emitted in light as the form of photons, it's emitted as a mechanical or kinetic energy. It's like an overexcited dancer who bumps into all their friends on the dance floor at the party. The excited bond stretches and twists and vibrates more, thus bumping into its neighbours, therefore passes its extra energy out harmlessly as heat energy to its neighbours. There are also sunscreens that contain semiconductor crystalline materials like zinc oxide. Quantum mechanics saves the day here too. When you pack billions of atoms together in a crystal lattice, some of their energy levels can overlap to form continuous energy bands. You start with a completely full valence band at the bottom and an empty conduction band at the top, with a forbidden gap in between. For zinc oxide, this gap is about 3.3 electron volts. Since visible photons have a much lower energy in this, they literally just pass straight through, meaning that the material is transparent. UV photons, however, can carry more than the 3.3 electron volts. This means that they can be absorbed in the valence band, kicking electrons up into high levels within the conduction band. These electrons slide down through the conduction band until they reach the very bottom of it. They lose their energy as heat to the lattice around them as they go. These electrons are now in a position where they can take the final leap across the forbidden band, releasing all 3.3 eV as heat into the lattice. We've seen two quantum mechanical based methods that stop us getting burnt in the sun. Either way, sunscreen doesn't work by mysterious blocking or a whole bunch of tiny mirrors. It uses the wonders of quantum mechanics to help.